We're going to start in just about a minute here. Okay, it's 1 o'clock. We're going to start. Well, hello, everyone. Welcome to today's session of the Siemens Advanced Robotics Series. My name is Brian Shea. I'm Portfolio Development for Siemens Manufacturing Engineering Solutions, and I'm going to be the host for today's event. Max, could you give me the next slide here? So today's seminar is session 6 of this series on advanced robotics that we've been running. The purpose of this series is to highlight some of the more advanced features of the Siemens robotics solution. And our session today is not about a particular software feature, but it's more about a technique for robotic spray coating that was developed by one of our manufacturing solution consultants here at Siemens. And in fact, our speaker today is Max Kirkpatrick, and Max is the person that developed this technique. So he's going to be showing that to us today. Max, can you give me the next slide here, the agenda? So this is our agenda for today. I'm going to point out that the session is only 30 minutes long. We're trying to keep them short, kind of a lunch and learn type of atmosphere. So what we're going to do is we're going to answer questions in the chat as we go along. So if you have questions or comments, just enter them into the chat or in the Q&A areas, and we'll attempt to answer that as we're presenting here. And if we have time at the end, we'll answer any remaining questions. Now, I should mention that the software, the simulation software that Max is going to be using today for this presentation is the Siemens Process Simulate application. So with that, I'm going to turn it over to Max.
Okay, thank you, Brian. Let's see. So if I can't get this to the next slide. That's always great to see. Let me just pull back up the presentation here.
Okay.
Not quite sure why that happened. I just tried to go to the next slide here. So. Okay, cool. So yeah, my name is Max Kirkpatrick. I'm a manufacturing solutions consultant with Siemens Digital Industries Software. And today I'm going to be talking about using Process Simulate to do robotic spray coating processes. And these could be things like additive processes, arc spray coating, or even just painting the surface of the part. The same sort of processes will apply for all of them. I want to touch on 4 main areas of this process: the cell layout process, path generation, robot programming, and then to simulation and download. First area I want to touch on is cell layout. And this is mainly about determining where we should place our robot, our fixturing, how we should hold our work, and how do we determine that that's going to actually work the way we expect it to when we go to actually push this to the real cell. So I'm going to jump into some live software here. This is the Siemens Process Simulate tool. See here. Having some technical difficulties here. It's rather slow. That's impressive. Twice in one day.
That's okay.
Just going to restart that real quick. And then I'll try to speed up here to see if we can't make up some of the lost time. Okay, so I'm just going to open back up the cell, and then we're going to get going again here. So first thing I wanted to talk about was cell layout. So how do we determine where these fixtures and fencing and everything should be in the cell? One of the first things we can do is analyze how the robot is actually going to move around in the cell. So we can use the inverse kinematics tools inside processing to understand how the robot will move in the space, how far it can physically reach if I start dragging around the end effector. And we can get a better understanding of what our robot reachability looks like at a certain height. But this is a sort of imprecise tool. So something else we might do is use what's called a reach test to do this. So I could take a look at maybe this first pass of my spray coating application and the last pass. And then we can analyze whether or not these locations in these paths will be within reach of the robot. Right, so I can take these two operations and then perform what's called a reach test. So we'll do a reach test, and in its current location, the robot can reach all these targets. So that's all well and good. That's because this is placed where we expected it to be. If I go to try to move the robot while I'm doing a reach test, we'll see that the menu is actually interactive, and I can dynamically move the robot around, and we'll see as I slide it farther and farther away from the fixture, the points turn from yellow to red, telling me that they no longer can be reached in the current position. And this is because the robot physically can't get to that location. This isn't taking into account the rotary positioner. So if we wanted to analyze whether or not if we rotated the positioner, if it would still get us there, we could actually do the same thing. We could pull up this rotary positioner and then rotate it to a new position. We go here, joint jog, move this to a new target, maybe something like this. And then we can do the same reach test and see if we can reach those targets now. Right, so in this position, looks like we can get everything except now we can't get the front leading edge of the wing. Sorry, of the blade here. It's a helicopter blade. And so these targets are out of reach. These yellow targets are ones that we can reach the Cartesian coordinates of, but we can't reach it in the correct orientation. And so the reach test tool just allows us to try to move stuff around to figure out where it should actually be positioned so that we won't have any problems with our cell later down the line. That said, I'm going to move this back to where it started, and we can sort of move on to the next thing here in our presentation. So once we've done some reach testing and cell layout, we've moved around our components to wherever they need to be in the cell, when we feel pretty comfortable with our cell design, we'll move into path generation. So the idea with cell layout is just determining or potentially reusing an existing layout to ensure reachability and collision-free paths. Next thing we'll look at is path generation. So there are sort of two approaches we can take to path generation. One of them is using an external tool like Siemens NX or any other CAD package to generate your curves that you want the robot to follow. And another is to generate those curves natively in Process Simulate. I'm going to show you both of those options here. So the first option I'm going to show you is generating the curves inside NX. So I've got this same blade. This time you can see I've got these curves that I want the robot to be able to follow on the surface of my blade. Those were created by creating a sketch on an offset plane and then projecting these lines down onto the surface to generate my, my coverage pattern. There are certainly more sophisticated ways to do this. You could generate these using your favorite tool and your favorite CAD package and then load them in the Process Simulator. Once we have a toolpath that we like, however, we can go to File, Export as a JT. And JT is the file format that Process Sim works with natively. And when we export this, we're going to export it as a single file and make sure we're including wireframe. And so wireframe entities are these lines themselves, and those will get loaded into Process Simulate. Once we've exported from NX, we can actually see those appear inside Process Simulate. So I'll just switch over to a part where we've already done this. So here's the same part, but this time from NX with the curves on the surface. And you can see they exist on both sides of the part, actually, because when we projected onto the surface, we projected onto both sides, right? So this is the method of generating curves from NX. Once we have these, we then can use them as what's called manufacturing features inside Process Simulate. So I would use this tool here called Create Continuous Manufacturings from Curves. It asks me what curves I want to use. I'm going to just select my curves from inside my model. Auto populates these. These names are created inside NX, by the way. So if you would like these to be a little bit more structured or easy to find later, you can name them as you want inside your CAD package. And make sure these are assigned to the correct part. And then we'll click OK. And what's going to happen is Process Sim will generate a set of curves. Someone can't hear me? Am I coming through fine here?
Yeah, I think you're coming through fine.
Okay. So I've generated a set of curves inside Process Simulate. You can see they're over here in my manufacturing features. And now if I hide the original curves from the CAD model, we can actually see those all on top of the surface of the part inside the Process Sim model. These will be the actual paths. They're called manufacturing features. These will be the actual paths that the robot is going to follow when we run these back. So from here, we create what's called a new continuous feature operation. Select our robot. We can give it a name if we like. And then our tool and our scope. So I'll click OK. And this creates our operation. So this is like our container that's going to contain all of the paths that we want to trace. Then in order to generate a path that the robot can follow, we have one last step, and that is to project this curve onto the surface. So we use project continuous manufacturing to grab the surface normals at each point. We're going to do tolerance-based spacing, and this is going to give us a maximum tolerance of, in this case, 0.05 millimeters. So robot will deviate no more than 0.05 millimeters from the path, and then we can project. And when we project, we're actually creating a robot toolpath that the robot will be able to execute. This takes just a couple seconds to run, and then we'll line up with all of our points on the surface for our robot to actually trace. Okay, so we can see the targets now inside Process Simulate. Each one of these points, each one of these frames here is a robot position, a robot target. We've generated our paths across the surface according to our projection parameters that we specified here. Now we can do things like put our robot at the first position and see what the path would look like, right? We could take our very first operation in this path. Actually grab this one and simulate just one pass. And so right now we're moving the robot without moving the table. And it looks like for this first pass, that's going to be good enough. But that might not necessarily be what we want to do. So we also can incorporate the rotary position limits. But before I do that, I want to show you the other way of generating a path inside Process Simulate. So we've gotten to the point where we have an executable robot path using features from NX. The other option is to generate paths using curves inside Process Simulate. So I'm just going to hide all these features that we just created. So we're going to do this once more, but this time we're going to generate the curves from inside Process Simulate using the continuous process generator. I'm going to select my target face and a start point and an end point for my spline. So let's say I want to start here and I want to end here. This generates my first curve. We can take a look at this from the top direction. Maybe I want to move this a little bit so it's a little straighter. Go. Something like that. And now I can say what my spacing should be. I happen to know for this gun, I want a 20 millimeter spacing and how many passes before and after this, right? So if I click here, say I can generate more. Maybe I want 30 passes. It'll auto generate me 30 passes here. So I'll just fill up this skin with the number of passes I want to get the coverage I need. I can specify what operation I want this in, and then I can click OK. And this will automatically generate those continuous manufacturing features that we were talking about before, except this time they're all native inside Process Simulate. From here, the process is exactly the same. I just project these points, and we wind up with, again, paths that we can follow on the surface of the skin. So here we can see we're moving down and back and down and back, zigzagging the way across the part. And if we wanted to, we could take one of these paths and we could simulate this like the first one here. Play and look and see what our path would look like. So this is how we do path generation. And the idea here is to generate or import coverage curves for robotic programming. Our next step is to actually perform the robotic programming and specify all the necessary parameters to create a program and download to a robot. So I'm going to move back to a path where we've already done some of this because there's well, I'll show it with this one. So we've got our continuous robotic op that we've created using the process inside Process Sim. I'm going to work with the one inside Process Sim because it's just a little bit lighter weight, a little bit fewer points, so it should be a bit easier for us. I'll load that up in my path editor. The path editor is where we can specify all the necessary parameters in order to actually download this to a real robot. And the very first thing we might want to do is have our positioner get influence. So right now, we are actually just moving sort of along these curves, but we aren't actually rotating the manual, the positioner, in any meaningful ways with it. So a couple things. In order to incorporate that, first we need to make sure the orientations are all correct on each point. Right? So we have some of these, you'll notice these are flipped as we sort of switch back and forth, each switch back. So what I can do is just set all of these to match one orientation. So I'm going to select all of my curves again. Sorry, all of my points. And then I'm going to use a command called align locations. We're going to align all of these to just this first target. Say okay, and that'll flip all these to match the right direction. Unless, of course, Process Sim decides to crash on me. Okay, I'm gonna spin up another one while this goes. Do apologize for the technical difficulties here, guys. What I'll do here is I'll just jump ahead past the alignment step to show you the results here. So once we have these paths aligned, we'll wind up with something that looks something along these lines where all of the orientation vectors are the same. From here, we then can do our what's called continuous positioner, or rather control our continuous positioner. So this is going to adjust our manual. So select all my paths and then use this tool called Part Continuous Positioning. And what we do here is we specify a target direction and a position. To specify the target direction, first I want to position my robot at the angle I would like it to hold. So for instance, if I start at this position, this is the angle that I asked my robot to hold for this path. So I'm just going to rerun this positioner tool in this location. So I move my robot to the starting location, make sure it's in a pose that is reasonable and would work for the entire path. And then I specify my target direction as the robot's current TCPF. That is this frame right here at the end of the arm. I make sure my positioner is selected and my normal and movement vectors are correct, and then I can hit apply. It's going to automatically run through and calculate external axis angles for every target. And then I can play back the path and we can take a look at what this would actually look like. And so now we see the positioner moving continuously as my robot arm swings back and forth across the part. There's a few other things that we want to be able to specify here. We'll jump back into the path editor real quick and I'll show you here. We need to specify, in the case of this robot, this is a KUKA robot, so we need to specify a tool and base frame. These would sometimes be called U-frame or U-tool on FANUC, or there's a number of other terms for them, but they are the end of arm tool frame and the reference frame for all the coordinates. We also need to specify what's called a zone, and as well as a motion type and speed. Once we have that stuff set, we can actually create a robot program from the path that we are simulating. And so you can see in these paths, they've all already been set. So once we have simulated and we like our path, the only other thing that we should do is take a look at coverage. So this is the robot programming portion, where we are going to create and refine robot programs based on our coverage pattern. And then finally, we need to actually simulate our coverage pattern, right? Simulate what the spray pattern is going to look like and download to the actual robot. So in order to simulate this coverage pattern, we first need to create a mesh on the surface of this part. I've already done this, so you can see that there's a mesh defined on this part. I can actually show you what that mesh looks like. So here is the mesh on the surface of this part, all these tiny triangles. This is going to be what we're using to determine what areas have gotten covered by spray and what areas haven't. So I'm going to hide that mesh again, just for performance reasons here. And then inside our program, we specify that we want to turn on our spray brush here at our very first location. So we set our brush and then we open the paint gun. And so now we can take a look at what the coverage would look like over the path. So turn on cover during simulation and play. And now we can watch our spray pattern appear on the surface of our part as we simulate. And this gives us a better idea of what areas of the part are being covered, what areas of the part are being covered twice, you know, how even is our spray, is the spacing what we wanted, are the areas that are getting missed, these sorts of things, right? For instance, this little bit here got missed by those two paths, so we might have to add or adjust our path so we move a little bit farther outside the area of the wing. Now, this simulation is a little bit slow, especially because we're running with all these points displayed and we're trying to do simulation with coverage in real time while sharing the screen. So I've got a pre-recorded video that shows you the result of that. I'm just going to pull that up real quick. You can take a look at what this would look like in real time. So this is how fast the robot would actually be moving, as well as simulating the cables and the coverage here. This was captured inside Process Sim using the movie recorder functionality, which makes sure that the simulation actually plays back in real time as opposed to in simulation time. Okay. So this is just to give you a sense of what this process would look like if we actually downloaded it. From here, all that's left to do is teach a configuration for each point, which we can do by using the auto teach functionality. And then it'll select the solution for each point. You can see for KUKA, these are represented by these S and T characters. We do S2T34, and that would probably be the same for the entire path. Once the path has been taught, we can actually just right click on the path and do a download to robot, and it will generate a .src file in the case of this KUKA robot, or a robot program in the file format that is appropriate for whatever robot you're trying to program. I'm going to jump back over into the presentation here, but that is mostly what I have. So idea around, again, simulation and download, just we want to simulate our robot motion and spray patterns, and then finally post-process and run these on real equipment.
Okay, so we got a couple of minutes here. So Max, I had a question here. Does this technique work depending on various brush spray heads, types and sizes, or is it dependent on a certain size of head?
Absolutely. So this is all adjustable. This cone that I've selected here is just defined in CAD, but we could totally change this to be whatever size spray, whatever matches your particular parameters. This is a relatively small one because the process that we were simulating here is a additive spray process where those cones are very small. But in the case of a paint spray, that might be a much bigger brush. That is just defined by the geometry of the cone that you specify, and you'll have to specify that, with your CAD package, or maybe you would figure that out by testing the component, etc.
Okay, we're getting some more questions coming in here. I'm going to, I think we got a little bit of time here.
Sure.
How about this one? Is the simulation software compatible with other platforms such as FANUC and ABB?
Absolutely. Yep. We fully support FANUC and ABB programming. We have post processors for both of them, and we can interpret and download to those machines. Yep.
How about this one? How do you control the airfoil leading edge coating thickness?
Right. So here, where we are coding this leading edge, right, and you see this simulation isn't doing the best job of it. We're actually getting overspray and underspray patterns at every cross path. One way we might control this is by having the airfoil complete a complete rotation every time, as opposed to doubling back and forth and back and forth. But as far as the spray thickness, what we're doing inside Process Simulate is simulating the number of times a certain area has been covered by the spray head. We aren't actually simulating a material deposition process. So what we're seeing is the number of times this cone has passed a certain area on the wing, or an airfoil or whatever you're trying to spray. The actual thickness that you'll wind up with is going to be dependent on the parameters of your spray nozzle and your spray system.
Okay. Well, let's see. We got time for one more question here. It says, for the example you have, how do you control the profile delta between the real part versus the design part?
So if this surface wasn't quite what I thought it was, right? So if I had an as-built part here that was actually slightly different than my as-designed part. One solution is to use a 3D scan of the as-built part as your design part inside the simulation. The other thing that we can do is a lot of times the profile will be very similar, but the positioning may be different. And we can use U-frames or U-tools or any number of offset calibration techniques available inside the software to find the surface in the correct spot and then base our spray on that. I've also worked on projects where we've actually done a live reconstruction of the surface, but that is a little bit more complicated than what we're getting into here. So this is mostly for programming an unknown surface.
Okay, Max, we're running out of time here. Could you pop the PowerPoint back up that's got it's got my yeah. The one before that, I think, it's got my email address on there. So we're running out of time. There is some additional questions here. We'll answer those by email after the session. But this particular session is this is the last of the Advanced Robotics series. So if you'd like copies of this presentation or a link to the recording of it, just let us know and we'll be able to get them to you. If you'd like copies of the previous presentations or recordings in this series, let us know. And I want to let you know that this series is going to be followed by two new educational series from Siemens. The first one is called Closed Loop Quality. This is a series of 8 sessions. They're each 30 minutes long, and they're going to cover manufacturing quality from end to end. The first session in that series is next Wednesday, April 14th. The second series of seminars is on line planning. And those sessions are going to cover the planning of manufacturing lines, including layout, optimization, and documentation of the manufacturing processes. So if you'd like to be invited to any of these seminar series, contact me. My email address is on the screen here, or you can contact your Siemens representative to get an invitation. So with that, I'd like to thank you for joining us today. I'd like to thank those of you that have joined us throughout this series, and have a great day and have a great weekend. Thank you.